Good. So I'm the last talk between you and lunch. There will not be too many equations. As the chairman already introduced, I will talk about polaritons, and I will talk specifically about polaritons and carbon nanotubes. So I think I need to first introduce the material that we're working with here a little bit. So I will briefly introduce single-walled carbon nanotubes for those who may have not been so familiar with them, and then we go through the different types of polaritons that we can actually create with these nanotubes. So nowadays it's very simple to describe a carbon nanotube. All of you know graphene, and now we imagine graphene to be rolled up into a tube. And you can do this in different ways. Obviously, it's not the way carbon nanotubes are actually created. They are grown in a CVD process usually. But conceptually, you can roll them up. This is just the simplest way of rolling up a graphene sheet. And you will then get different types of carbon nanotubes. And the way this is described in the community is by a vector notation called N and M. So we assume we have these unit vectors, and you can then basically count along your graphene sheet, your honeycomb sheet, in one direction and the other direction, and then you get these vectors N and M, and you basically roll up the sheet in this direction, so along the red arrow here. And then you get, as I said, you get lots of different carbon nanotubes from this rolling up procedure. And here are just a few examples. There are actually two types. One of them is the zigzag nanotube, and one of them is the armchair nanotube, which are actually not chiral. They have a mirror plane. And then essentially all the other ones, they are chiral. And this leads to this slightly misleading, at least for chemists, very misleading nomenclature. Some people say these are different chiralities. Yes, these carbon nanotubes are chiral, but the mirror image is not, for example, the mirror image of this is not this. Yeah? So these two have no chiral relation to each other. Yeah? The mirror image of this would be called the 5,6 nanotube, but has more or less the same optical properties. So you can see there are lots of different structures that you can get from rolling up this sheet of graphene. And this is nice, but this is also a problem, because of course when you grow these carbon nanotubes, you get all kinds of different types in one sample, and this is not what you want. Just to describe how you then get from the graphene wave function to actually to the carbon nanotube wave function and band structure, when you do this folding or this rolling up procedure, you basically create new boundary conditions, and in the simplest model you basically have these cutting lines that come from the boundary condition, and they cut through the band structure of the graphene, and you then basically get the band structure of your carbon nanotube, and from that you can get the density of states. And very simply speaking, whenever such a cutting line actually goes through the K point of the graphene, you get a metallic carbon nanotube. And when none of these cutting lines go through the K points, then you get a semiconducting carbon nanotubes. And for symmetry reasons, you always have, if you take a sample of carbon nanotubes, you have 2/3 semiconducting and 1/3 metallic. So again, you could say this is nice, or you could say this is a problem. If I have a material that can basically have a large portion that is metallic and a large portion that is semiconducting, for example here with these two nanotubes, I only want one or the other. Yeah, I want metallic nanotubes for maybe, I don't know, cables, or I want semiconducting carbon nanotubes because I want to do spectroscopy. And if I want to do spectroscopy, ideally I want to have only one type of carbon nanotube. I only want to have, for example, the 7,5 nanotubes, not all the other semiconducting ones. And this has been a huge problem for the last, or since the discovery of carbon nanotubes. But this problem has been solved basically by lots of different separation techniques. There's density gradient, ultracentrifugation, chromatography techniques nowadays. And the technique that we are using is selective polymer wrapping, which is very simple. So the way it works is you buy a powder of carbon nanotubes. They're commercially available nowadays. You have a dispersant, can be different ones. A solvent can be water or maybe toluene. You ultrasonicate to break up the bundles of the carbon nanotubes. Then you centrifuge, and then the whatever is still bundled ends up at the bottom of your centrifuge tube, and you get a supernatant. And very often this supernatant will look black. Yeah? Why does it look black? It looks black because lots of different carbon nanotubes are in them, because each particular chirality or type of nanotube actually has a very specific color. So if nothing else, I want to convince you carbon nanotubes are not black. So this is schematic, but these are actually samples, it's not from our group, it's from a different group, of separated carbon nanotubes, and they all have a different color, in the visible even, and of course also in the near infrared. But of course, if you mix all of them together, then you will see a black dispersion. Yeah? So what you want to see is something like this, a nice bright color, one single color. Okay. And the way we do this, as I said, we use polymer wrapping. It's a very simple process. I could teach you within half an hour how to do this, and if I give you the right materials for that. So we use ChromoCard nanotubes, again, commercially available carbon nanotubes, a commercially available polymer, a PFO BPY. We don't use sonication. We use shear force mixing for breaking up the bundles, but that's a technical detail. Then we centrifuge, and we get this dispersion. And you see from the color, the bright purple color, that this is one type of carbon nanotube. So the polymer that we use is actually colorless. Yeah? So you see that this solution is colorless, and now we have these, this purple solution. It's purple because the 6,5 nanotubes absorb green light, and so you get this nice purple color. And this is not, I mean, I also want to convince you, this is not a technique anymore where you get tiny amounts and like you have a tiny vial full of material, but you have actually quite a large amount of material. And this shear force mixer in my group runs every day, so we produce these solutions every day. Good. So we want to use, carbon nanotubes have many different interesting properties. One of them is, of course, charge transport. They're very good for charge transport, but they're also near-infrared light emitters. Not very good ones, unfortunately. They emit light in the near-infrared with very narrow line width. It's an excitonic emission, which is, here is oversimplified because it looks like a band-to-band transition. It's not, it's an excitonic transition. You usually absorb in the so-called E22 regime, which is in the visible most of the time, and then you emit in the near-infrared. Unfortunately, the quantum yield of carbon nanotubes is pretty bad. This has to do with the large mobility of the excitons in the carbon nanotubes. So usually, even in dispersion, you have an efficiency of less than 10%, which is terrible, actually. So our 6,5 nanotubes, they, as I said, they absorb light, green light, so around 575 nanometers, and they emit around 1,000 nanometers. Yeah, with in dispersion with a line width of, if they're really well dispersed, 20, 25 nanometers. We optimized our dispersion process so that the photoluminescence yield is as high as possible. So this is why we use the shear force mixing. This produces very long carbon nanotubes, and the length of the nanotube determines to some degree how emissive they are. And we get to about 2.3, 2.4% in dispersion. If you then, from this dispersion, create a film, for example, like this could be spin-coated, it can be aerosol jet printed, or produced by filtration. So for example, this is produced by filtration. Then the photoluminescence yield drops quite substantially to 2.1 to 0.3%. You also get some broadening. So the orange line is the dispersion, and the green dotted line is the film. Here you see this E22 or S22 transition in the visible, here the E11 or S11 transition in the near infrared, and we also have a phonon sideband, not unlike a molecule, for example. Okay, so these are the basics of basically photophysics. These are very simplified photophysics of carbon nanotubes. There's a lot of other things you could talk about, dark excitons and so on. But now let's go to the exciton polaritons. So there has already been some introduction about polaritons, and we already saw that a lot of you already know what it is. Very briefly, I will talk about polaritons in a cavity, in a Fabry-Perot cavity. So we have two mirrors. They have a distance of maybe lambda half or maybe lambda quarter. And so we have our cavity photon. Its lifetime is determined by the quality of the mirrors, essentially. And then we have our exciton, and that has more or less no dispersion. And if the coupling is strong enough, we form exciton polaritons. So we get anti-crossing, we get a lower polariton here, and an upper polariton here. And the distance here, the energy distance, is called the vacuum Rabi splitting. In the classical picture, you could maybe imagine that the exciton emits light that is reabsorbed and so on. Or, of course, in quantum mechanics, you create basically a new quasi-particle with two states. The condition is, of course, that the coupling has to be much faster than the decay of each component. So you have to have a good cavity, so the cavity photon lives for a long time, and you ideally maybe also want to have an exciton that doesn't decay right away. We can actually get to both of these conditions. You also get more coupling if you have more oscillators. So here we have the oscillator strength, but also the number of oscillators, and this is the mode volume. And you can increase the cavity lifetime by basically using better mirrors. Maybe instead of gold mirror or silver mirror, you use a DBR mirror. This is old. We've already seen that people have done this I don't know, for 20, 25 years, especially in these quantum worlds, maybe in gallium arsenide or cadmium telluride. There, the problem is that the exciton binding energy is very low, so you usually have to work at cryogenic temperatures, 4 Kelvin. Then, I think maybe like 15 years ago or so, people realized that in organic materials, your excitons live at very high temperatures because they have large exciton binding energies. So you can observe strong coupling at room temperature and also observe condensation of polaritons at room temperature. And recently, of course, as always, the 2D materials have come up as well. They also have a high exciton binding energy. They also have a very large oscillator strength, so you can actually create polaritons in a single layer of, for example, molybdenum diselenide or molybdenum sulfide. Okay, so why carbon nanotubes now? They also have a very high oscillator strength in the near infrared. We have the large exciton binding energy, which mainly comes from the dimensionality, a narrow line width, which is always nice, especially from an experimental point of view, and a very small Stokes shift, so absorption and emission overlap very nicely. So all of these are great, and plus carbon nanotubes can conduct current. Yeah? So you can do electrical pumping, which I will show you in a moment. So the first thing, of course, is you have to make a cavity. Yeah? So you have to have a film that has the optical quality, so you can just evaporate some gold on top, and you then have the proper cavity. So this is why we needed to actually scale up this purification of the carbon nanotubes, because we needed enough nanotubes in this cavity. So this is what it then looks like. We just used a simple gold mirror. We spin-coated a film of this dispersion polymer with the carbon nanotubes, and then basically evaporated gold on top. And because I will show you some data later, the way it's done when you spin coat is that if you do it essentially with a very viscous sample, you will get a variation of thickness of your film across the sample. So you basically have a different cavity at each spot, which is what we want. Yeah? So the experiment is fairly simple in the end. Then we do angle-resolved spectroscopy, so we use Fourier imaging to actually, at each point of our sample, determine the reflectivity, angle-dependent reflectivity and energy, and then also photoluminescence from the same spot. Yeah? So all the data is always taken from the same spot, respectively. If you don't have any carbon nanotubes in your cavity, but just the polymer, then you have just the cavity photon. And so we use this to determine what's the quality of our cavity, roughly. And you would, of course, expect, if you have a simple Fabry-Perot microcavity with lambda half or something like that, that you would see a parabolic dispersion here. So this is just angle coming from the microscope objective that we're using. So if you now change the thickness of your film, you see how this cavity dispersion is basically just moving in energy, as you would expect. Yeah? So this is the typical thing. The dotted line here is where we would expect our exciton for the carbon nanotubes. Now we put the carbon nanotubes in, or well, I should say the quality factor is terrible. But that's thankfully no problem for us. Now we put the carbon nanotubes in. So here again, this is where the exciton should actually absorb and emit. This is reflectivity. Yeah? And you see, first of all, that this is actually the lower polariton. It has this, this shape where it basically kind of tapers off at the end. And here you start to see the upper polariton at the upper edges. And if I'm now changing the thickness a little bit further, you can see the upper polariton much better. And you can also see that they never cross the exciton line. Yeah, so this is the anti-crossing that we want to see. Yeah? So depending on the thickness, whoops, I can go basically through these different positions for my lower and upper polariton. You can model this, of course. You can either do just a very simple Hamiltonian and just model the lines, or you can do a proper transfer matrix simulation where you can also see the intensity and so on. So I think you can see that this fits very well with the model, and we can calculate the coupling strength from this, and our Rabi splitting here is 114 millielectron volts. It of course depends on the exact sample. So we're definitely in the strong coupling regime. We can also calculate the fraction of exciton and photon in the lower polariton. So here you can see that, for example, at 0 angle, the fraction of the exciton here is a little bit below 50%, and the fraction of the photon is a bit above 50%. Okay, so this was reflectivity. What you usually want to see is emission. Yeah. So of course we excite our sample with a laser, and so now we see photoluminescence. Yeah, photons leaking out from the cavity here, and what you should see, or what you would expect maybe, is the emission should always come from the lowest state. So and this is the lower polariton, and this is what we see here. We don't see any emission coming from up here. And again, if we go through the different thicknesses, we can see that we actually don't see the upper polariton anymore. We only see emission from the lower polariton. Yeah? And this is to be expected if you have decent relaxation of your polaritons to the lower polariton state. Okay, good. So again, we can compare this. The emission really comes from the lower polariton state, and we don't see any emission from the upper polariton state. Okay, so since we had these samples where you can basically change the cavity all over the place, and then we also made a couple of different samples with a different concentration of carbon nanotubes, we could maybe kind of map out a little bit the relaxation states. For example, here you see when you have a very low concentration of carbon nanotubes, you see a lot of emission coming from higher angles, which basically means you don't get good relaxation. It's kind of called the bottleneck effect. Why this happens, we are not quite sure. Certainly when you go to higher concentrations, it disappears, and you get fairly good relaxation of your polaritons. Yeah, and this is something we're trying to figure out at the moment. What are the photophysics behind here that the relaxation is so much better when you have actually a lot of contact between the carbon nanotubes? Usually, most people would say, I want to separate my carbon nanotubes in order to get better emission, but here we want them to be close together. I should say, well, I think I showed in the beginning, these nanotubes are not aligned in any way. They are more or less flat in the plane, but they're all over the place. Yeah, so there's no alignment. Okay, so my group is more of a charge transport group, where we're only on the side optics group. So we want to do electrical pumping of polaritons. So what do you have to do that? So this is our cavity with the carbon nanotubes in them, very low concentration. Okay, let's conceptually, let's squeeze all our carbon nanotubes in one plane. We can do that experimentally. Then we add some electrodes, left and right, source and drain. And now we have, if this is a dielectric and this is a dielectric, up here we have a transistor, actually an ambipolar transistor that can emit light. And here, this is our cavity. And then we can electrically pump our exciton polaritons in this structure. And the nice thing about this is that, unlike, for example, in a light-emitting diode, we completely decouple the charge transport from the cavity. Yeah? So the cavity is this here. Yeah, and I can change that. I can make it larger or smaller. But the charge transport is in this direction, and is not much affected by what's going on down here. A little bit what's going up here. Yeah? But this we have very well under control. So yeah, so a light-emitting field effect transistor structure here separates the cavity from the charge transport. So the way it works is that you take a substrate, or actually I should say this is a light-emitting field effect transistor. You have a substrate, you have your source drain electrode, you spin coat a film of carbon nanotubes, a very dense film. We then have a hybrid dielectric of PMMA and hafnium oxide and a top electrode. And this gives you ambipolar transport. You don't have to, for those of you who are not into transistors, it doesn't matter. Just remember, you create excitons with this. It has fairly high mobility, a good on-off ratio, so it all works. And if it works, then you can actually see, depending on the applied gate voltage, you see light emission coming from the channel of the transistor. And the way it works is that you basically inject holes from one side and electrons from the other side. They meet and they recombine and they form an exciton. Yeah, and this is what you see here. I can also just keep the gate voltage constant, and then this emission zone that is moving here will just stay somewhere in the middle, and then I can do spectroscopy on it. Yeah? And it's fairly stable, so these, you can see that these transistors don't actually change very much over time, so you can really do spectroscopy on it. We then placed this whole transistor in a cavity. As I said, we just basically included a bottom mirror and a spacer layer, so we calculated the thicknesses they had to have. With or without cavity, the electrical properties are the same, yeah? So which is very nice. We were worried about a floating gate, but this was not the case. And then we checked whether we still see strong coupling. So yes, we do. So we have the reflectivity here. It's now a bit noisy because there are all these electrodes as well. So we see strong coupling here, 127 millielectron volts of Rabi splitting. We see photoluminescence coming from the lower polariton, and now we just switch on the light emitting field effect transistor, and we see the electrically pumped exciton polaritons coming from where they should come from. Yeah? We can actually pump these exciton polaritons at very high current densities, 18 kiloamps per square centimeter, if you calculate that. I'll show you a picture of that. And we also can look at the thermalization of the polaritons, which is important if you want to go to condensation, and they actually thermalize better than the optically pumped ones. We're also not sure what's the reason, but of course the creation of the exciton polaritons is different when I create them electrically from optically pumping them. Very briefly, here you see that the emission essentially doesn't change whether you work at low or high current density, and this probably has to do with the fact that actually the charge carrier density is minimum here. However, there's a second thing you can do in such a transistor structure, and that is by changing, the simple idea of a field effect transistor is that you accumulate charge carriers. That's the point of a field effect transistor. When you accumulate charge carriers in a material like carbon nanotubes, or actually in any other material as well, you usually deplete the ground state level. Yeah, because you basically charge your carbon nanotube, and the charged nanotube doesn't absorb anymore where it used to absorb. So you should actually lose your oscillator strength. And this is what we can now do in our experiment. This is schematically shown here. So here we have all our carbon nanotubes. Now we dope them essentially electrostatically with holes, and then they don't absorb anymore. And so we lose our oscillators. And we chose a sample that was just about in the strong coupling regime. So you see the anti-crossing here. And then we applied a voltage. So we bleached the absorption, and now you can see that you go from the strong coupling regime into the weak coupling regime just by changing the applied voltage. Yeah? So you can reversibly, within the same system, go from strong coupling to weak coupling. Yeah? Recently there was a publication where this has been shown with 2D materials as well. So whenever you have a material that basically has this property that it loses its oscillator strength when it's doped, you can show this. And a field effect transistor is one way of doing this. And so here you can see how we basically change the Rabi splitting with the applied voltage, and then at some point you basically go into the weak coupling regime. Okay, so but bleaching absorption is kind of boring. Just you go from strong to weak coupling, that's not so interesting, at least for me. But there's another thing that actually shows up when you dope carbon nanotubes, and this effect is very strong in carbon nanotubes, but it's not only restricted to carbon nanotubes. You also see these so-called tryons in other materials. A tryon is a charged exciton. So if you charge your material and then you excite it, you actually get a charged exciton. And this charged exciton is usually, it's always redshifted. Not usually, it's always redshifted. It also shows up in TMDs. And the tryon here, this is an experiment in absorption with a very thick film of carbon